So hello everyone, I'm Norman Wildberger. Today we're going to carry on with this theme of just talking about these three very prominent French geometers, Meusnier, Monge, and Dupin, who lived around the time of the French Revolution, end of the 18th century, and had big input into the direction of differential geometry. So today we're going to talk about Gaspard Monge, whose dates are 1746 to 1818. And he lived in very exciting times and had a very interesting career. He was an ardent supporter of the French Revolution when it came about, and he ended up having very prominent positions in the French Revolution. He also became a friend of Napoleon in a trip to Italy, and became then a close associate to Napoleon. In fact, he accompanied Napoleon on his Egyptian campaign, went to Syria with Napoleon as well. He was not just a mathematician, but he was also a chemist and a physicist, and sometimes called the father of differential geometry, in fact, because he was an important teacher and professor. And he's also the inventor of descriptive geometry. Okay, that's a subject that's not taught in maths schools so much these days, but it's important for certain kinds of engineering applications. If you're doing draftsman kind of work, descriptive geometry is very important. So the idea with descriptive geometry is that if you have some object in three-dimensional space, let's say a plane, and maybe on top there's a cube here, and maybe from the cube there's a triangular wedge, something like this. To represent this three-dimensional object somewhat more faithfully, Monge's idea was to take three views of it, to take basically a view of it straight on, and then another view from on top, and maybe another view from the right. Okay, so there are these three views, which are sometimes drawn like this. Okay, so let's see, if we looked at this object, and I guess I should remove some of these lines because they're not actually visible if you actually looked at it. Be these dotted lines. If we looked at it from straight on, we would see something like this. That'd be that base there, and then there would be a box here, and then there would be something like this. While if we looked at it from on top, we would see something like a base like this, and then the box would be sitting here, and then there would be that triangular wedge in that direction. And if we looked at it from the right-hand side, we would see the base, and then we would see this see it like this. I guess those would be the three outlines that we would expect to see from the different positions. And Monge discovered this actually when he was in military college. So he was asked to create a fortification plan for a certain fort, French fort, and he used this kind of geometrical reasoning to solve practical problems in a much more efficient way than previously. So he basically discovered descriptive geometry for a military application. And of course it became a very important subject on its own right. It still is an interesting and attractive subject. Monge also dabbled in other things, so he's also known for a few important theorems that are also geometric, but there's Monge's theorem on circles, and Monge's theorem on circles is if you have three circles in the plane, maybe like this. Can you see them? I shall move them up here. So we have 3 circles in the plane, maybe here, here, and here. Then we can look at the common tangents. So these 2 circles have some common tangents here, which meet in this point called the homothetic center of the 2 circles. And these 2 circles have similar tangents which meet in a homothetic circle, a homothetic point. And then these ones also meet in a point. And Monge's theorem is that those 3 homothetic centers are collinear. And there's a kind of an attractive no computation proof if you think of this picture as being a 3-dimensional picture rather than a 2-dimensional picture. So if we imagine each of these circles as representing spheres, and then these are sort of equatorial lines that joining suitably placed equators of the various spheres, then the argument is that, well, you can find a plane that's touching all 3 spheres from below, and then also another one from on top. Okay? So if you just imagine sort of having 3 spheres like this, if you place a plane that's just touching 2 spheres and then it's allowed to tilt, well, then you could maybe tilt it until it touches the 3rd one. So that's a plane that touches all 3 on top, and then you can get another plane that touches all 3 on the bottom. And then the argument is that this line that we're creating is then the intersection of those 2 planes. And the reason is, well, that if you look at these 2 lines here, where they meet, that meeting point will also lie on the line in the top plane that's touching both spheres. So if you have 2 spheres and you draw all possible tangents from one to the other, then all those tangents will meet at one point. So if these 2 tangents meet at one point, then the top tangent will also meet at that point. And that shows that that line is on the top plane, and therefore that point is on the top plane. And then a similar argument shows that it's also on the bottom plane, and all these 3 points are then on both planes, and so they must be collinear. I can't help but mention another beautiful theorem of Monge, which has to do with the geometry of the tetrahedron, and it's the Monge point of a tetrahedron. So of course the tetrahedron is a 3-dimensional analog of a triangle, and so we would expect that because there's a very rich Euclidean triangle geometry, there should be a reasonably rich tetrahedral geometry. In fact, we know much less about tetrahedrons than we do about triangles, but still there's quite a lot of things known, and this Monge point is one of the highlights of tetrahedral geometry. So what it is the following, that if you define a mid-plane of a tetrahedron, so this is a plane perpendicular to one side, or edge, which meets the midpoint of the opposite side or edge. Okay, so such a tetrahedron has these 6 edges, which are naturally in pairs. So this edge is naturally paired with this edge because they don't share a common vertex. And so what a midplane is that you take a midpoint of one of the edges, and then you look at the plane that's perpendicular to the other edge through that midpoint. So you take the plane that's perpendicular to the other edge through the midpoint on the other edge. That's then a midplane of the tetrahedron. And it will meet somewhere, but not necessarily at the midpoint. And Monge's theorem is that all 6 mid-planes meet in a point. That's called the Monge point, and that's some kind of analog of the orthocenter. In general, a tetrahedron does not have an orthocenter. There is a centroid, yes. So if you just take the vector average of the 4 points, you get the centroid. So there is always a centroid. And there's also a circumcenter. There's a unique sphere that you can draw around 4 points. So there will be a unique sphere that goes through those 4 points, and it'll have some center, let's say C. And it turns out that this Monge point also lies on this line through the circumcenter and the centroid, so it's some kind of analog of the Euler line for a tetrahedron. And there's some fixed ratio, or maybe it's 1 to 3 here somewhere. There's a beautiful fact. If you're interested in the tetrahedron and interested especially in the trigonometry of a tetrahedron, which is still really an open subject, the trigonometry of a tetrahedron so many things are known, but still there are things that are unknown. And there's a rational analog of this trigonometry, which I've described in one of my seminar YouTube videos. So if you look on one of my YouTube seminars, I lay out a rational trigonometry of a tetrahedron in somewhat novel fashion, if you're interested. Okay, so those were some of Monge's contributions to classical geometry. But of course, he was also very interested in differential geometry, and he was a very important historical figure for that. So we've already seen that Monge was very interested in developable surfaces. So Monge really liked developable surfaces. And these had been earlier introduced by Euler, okay? And we remember we saw that that developable surfaces included things like cones and cylinders and tangent developables of curves. So if you have a curve and you look at all its tangents, then those tangents sweep out a surface which is a developable surface, the tangent developable of a curve. And we talked a little bit about Monge's study of a curve and some other surfaces that he considered in the context of studying a curve. But he also had a flexible attitude towards developable surfaces, and he realized that you could also obtain them or think about them in a quite different way. Okay, so Monge also considered developable surfaces as generated by one parameter families of planes. So this is really kind of dual. This is dual to the idea of to a one parameter family of points, i.e. a curve. So in three-dimensional space, I remind you that points are denoted projectively, well, Cartesianly by a triple x, y, z, or projectively by a homogeneous quadruple x, y, z, w. And planes can be described projectively in terms of L, M, N, and P, say, representing the equation Lx plus My plus Nz plus PW equals 0. Or if W equals 1, then you get just a standard plane. So the symmetry in the representation of points and planes suggests that there's something really fundamental, a fundamental duality here. And that's sort of manifested in Monge's view of the surfaces. So for his idea of surfaces, he said, all right, let's take a plane. So z equals, say, x phi of alpha plus y of psi of alpha plus alpha. So this is how he wrote it. So here's the equation of a plane in three-dimensional space, linear in x, y, and z, with coefficients that depend on some parameter alpha. And he decided to sort of make this alpha and then regard these as functions of alpha, which can be rather arbitrary functions. And as this parameter alpha varies, we have this family of planes. So maybe here's alpha equals alpha 0, and then a little while later we have alpha equals alpha 1, and then a little while later we have alpha equals alpha 2, and so on. So we have basically a one parameter family of planes, which I can show you perhaps just by looking at the paper. That's a plane. So if I just take an arbitrary family of planes, okay, we just look at a piece of it like this, then that's going to sweep out a surface. Okay, and one way of thinking about what's happening there is to think about sort of adjacent planes, or planes that are very close together. So that plane and the next one, okay? So very closely connected planes will meet in a line. So adjacent planes will meet in a line. And then the next ones will meet in another line, and so on. So adjacent planes meet in a line. And Monge realized that there's a clever sort of algebraic way of getting at that equation of a line. So one way that you might think is to say, all right, why don't we just take a nearby plane, which would have the form x phi of alpha plus h, say, plus y times phi of alpha plus h plus alpha plus h, where h is some small increment in our parameter. Okay, but if we're looking at the intersection of these two planes, that is the common solutions to these two planes, then another thing that we can do is we can take the difference between these two equations and divide by h. If we take the difference between these two equations and divide by h, then these coefficients here become essentially derivatives. All right, and so if h is very small, then an alternative to doing this or writing this down is just to write down the derivative, which would be 0 equals x phi prime of alpha plus y times psi prime of alpha plus 1. And this is how Monge got the lines. He would just take this first equation and it's essentially its derivative and remove alpha. Okay, so those are two planes, and where they meet is a line. So 1 and 2, if we solve that, we get one of these lines. But then he went further and said, well, okay, we can go a little bit further. If we're interested in this line as well as the next one, okay, another nearby one, then these two sort of adjacent lines are also likely to meet in a point. They are going to meet in a point because they're both lying on the intermediate plane. So there's a point here, say the point of regression, which can be obtained by a third equation by differentiating this thing once more. So if we differentiate once more, we get 0 equals x phi double prime of alpha plus y psi double prime of alpha. Let's call that equation number 3. And then if we solve for equation 1 and 2 and 3, solving 1 and 2 and 3 simultaneously gives this sort of edge of regression. So what happens is that as the planes sweep along, this red point sort of sweeps out some curve. Called the edge of regression. And it's a very similar kind of thing that happens when we are looking at curves and looking at normal planes to curves. And there's also a very sort of analogous sort of dual thing that happens there. All right, so this is a fruitful investigation. And Monge went further and said, well, that's one parameter families of planes. Why don't we consider one parameter families of surfaces? Well, so you have some equation, f of x, y, z equals 0. And at this point, Monge was taking this very algebraic point of view that we've adopted in this course, okay? Thinking of a surface as an actual algebraic surface given by an equation. And then said, all right, well, that's one surface. We can now introduce some parameter. So we can stick an alpha, whatever the coefficients we have, we can make those functions of alpha instead of constant. And then we have a family of surfaces, okay? And then you get a similar picture, but more complicated because the surfaces can be rather general. So there's surface number 1, and then there's surface number 2, and surface number 2.1, and so on. A whole family of them. And then we can think about their envelope. What do they sweep out? And well, they'll sweep out in general, some surface. So again, you'll have any two adjacent ones will intersect, but in a curve. And then you have these curves instead of lines, and you still might get a point of where those curves meet, maybe. And you get then this sort of surface, or that the one parameter families envelop. So maybe what I should say that, from this point of view, if you ask what is a curve, okay, so maybe you have a curve like this. It's a conic. A curve has the interpretation as being something that's swept out by a point. That's what you get when a point is moving. But there's this dual picture where it's also the envelope of a family of lines. And in fact, neither is really primary in some way. They're both completely reasonable ways of describing the same curve. An envelope of lines or a trajectory of points, pretty well the same thing. Maybe I should remind you, going back to the situation of a developable surface, which is one that's created by a one parameter family of planes. So I've shown you this before, but you may remember that if you take a piece of paper or cardboard like this and you suitably fold it, or not really fold it, bend it without actually folding it, right, you get something like this. This is a developable surface. And Monge realized that this kind of surface is really, there are lines here, and you can see the lines by just looking at the profile of the surface. So if you look at the profile of the surface as I'm turning it, hopefully you will see a straight line profile at all times. If you look up at the top here, the image of what you're seeing should be a straight line. Okay, so that's a property of these developable surfaces, that if I take one of these straight lines, okay, that the tangent plane for each one of those points is exactly the same. So the tangent plane at this point and at this point are exactly the same. Okay, so developable surfaces have this property, and that's also sort of a property you can think about them rolling they can roll on the plane, and as they do, they make contact with the plane, a line each time. So Ruben has made a picture of the oloid, graphics with the oloid, and one of the videos that maybe it's already up. Is it already up? No, it's not up, but it will be up at some point. Anyway, you'll see this oloid rolling down a hill, and you'll see the paint from the painted oloid transferring onto the plane, and you can kind of see there this aspect of this ruled aspect coming in contact with the plane, one line at a time. All right, so these were very favorite kinds of things for Monge, and he took this idea and applied it to a general surface, and some differential geometry was very important. So he really introduced the idea of studying lines of curvature. Okay, so if we have a general surface, we've seen that at a general point, in general there are two principal directions. So there's various normal sections, and there's two normal sections which are the most and the least curved. Okay, so these are the principal directions. So these are the directions of maximum and minimum curvature. And generally speaking, we have such two directions at every point on a surface, except when we're at an umbilic point. Okay? At an umbilic point, the two curvatures are the same. It's like a sphere locally. And in that case, there's no two distinguished sort of eigendirections. In that case, all directions have the same curvature. So if we avoid, except for umbilic points, these directions exist everywhere. And Monge realized that it was interesting to ask the following question. Are there any curves on the surface which are tangent everywhere to these principal directions? So at every point we have some principal directions. Okay, maybe I can draw them like this. And we always know that they're always perpendicular. Euler showed us that. And what we're looking for is a line of curvature. So a line of curvature, one that is a curve on the surface, which is always tangent to a principal direction. Well, if there are such curves, there are very likely lots of them, and there are likely going to be two meeting through any point. So we can expect a kind of grid of lines of curvature that covers most of the surface, except perhaps if we have some umbilic point, in which case we would maybe expect that the lines of curvature somehow go around them in some fashion or another. All right, so Monge said, okay, this is interesting. How do we calculate these lines of curvature for a given surface? Well, it's not that easy, but he wrote down a differential equation. And he also showed an important property of these lines of curvature. So Monge wrote down a differential equation that's satisfied by lines of curvature. It doesn't mean that it's necessarily easy to solve, but at least there's an equation out there. And he also proved the following theorem. That if C is a line of curvature, or if C is a line of curvature, on a surface S, then the one parameter family of normals to S along C form a developable surface. So the story is this. Here's some surface S, and we have lines of curvature, say like this. So these are lines which at each point are sort of as curved as they can be, maximally curved or minimally curved. They don't have to have the same curvature at every point because the principal curvatures will vary from point to point. But at any one point, you're going in the maximum possible curve direction or the minimal possible curve direction. All right, so if we take one of them, say this one here, then this surface has normals. Okay, it has normals of it at any point. At any point, there's always a normal line to the surface. But the crucial thing is if you look at the normals to the points on one of these lines of curvature, C, say these ones here, and you take these are actually lines, and you take the union of all those lines, that's a surface. And that's a developable surface. That's exactly the kind of surface that you get by taking a piece of cardboard and bending it suitably. If you take the normals along some arbitrary surface, you also get a ruled surface because it's ruled by the normals. But it's a ruled surface which is not developable. The developable surfaces are a very special kind of family within all the ruled surfaces. They're the ones that have curvature 0. Okay, so Monge knew this too, that developable surfaces are ones, well, in our language, that the Gaussian curvature, or the second curvature, is identically 0. So a natural question is, okay, what do these lines of curvature look like for something? And the simplest, the most perhaps natural thing to ask about is for an ellipsoid. So if we take an ellipsoid, x squared over a squared plus y squared over b squared plus z squared over c squared equals 1, where a and b and c, let's say, are distinct, then what do the lines of curvature look like? Well, I'll show you. I told you last time that such an ellipsoid has 4 umbilic points. There might be one here, and then sort of an opposite one on the other side, and an opposite one on the other side. So these are the 4 umbilic points. These are the places where the 2 principal curvatures are equal. All right, so now what do these lines of curvature look like? Well, they look something like this. This is probably not a very good picture. Okay. There's one family like this, and then there's another family that go like this. And come around the bottom one, and then another one maybe a little tighter. All right, so you should think of them as being somehow analogs of ellipses. So these are sort of like ellipses on the surface of the ellipsoid, with these umbilic points playing the role of foci. Okay. So I remind you that if you have in the plane, if you have 2 points, then there's all kinds of ellipses that you can draw that have those 2 as their foci. There's a whole range of them. And And the story is very similar. In fact, it's not just very similar, it's almost uncannily identical, because it turns out that you can create these lines of curvature for the ellipsoid by the following string construction. So in the plane, of course, there's a famous string construction that you get a piece of string and you stretch it tight, tie it down to the two foci. It has a fixed length. You stretch it tight, and then you move your pen around, and it sweeps out an ellipse. Okay, so you can do the same thing here. You can take a piece of string, and you can tie one end to this umbilic and then the other end to this umbilic, and then you tighten the string so that it's on the surface. So you take the third point and you put it somewhere, and you tighten it so that now the string is taut against the surface of the ellipsoid. Okay, that means that's some kind of like minimal path curve. That's going to be called a geodesic. That's another very important type of curve in differential geometry. Okay, so then what you do is you just move this fixed point exactly in the same way we do in the planar situation, always keeping this total length constant. And as you do, you will go around one of these lines of curvature. Say that. So the lines of curvature for an ellipsoid can be traced with a string tied to two non-opposite umbilic points of fixed length. And made taut against the surface. Making it taut against the surface means that that's actually a shortest curve. So it's a shortest path or geodesic on the ellipse. And then the locus of this free point is this line of curvature. So if we choose these two umbilic points, then we get lines of curvature like this. If we choose the ones in the bottom, well, then we get these other ones. But if we choose these two, then the ellipses kind of go in this direction, like the ones I'm showing here. They kind of go here, and then they loop around down there. In particular, these ellipses are always perpendicular, right? Because we know that lines of curvature are always in principal direction, so they're always perpendicular. So this is a family of mutually perpendicular rulings of an ellipsoid. So this pattern is one of sort of mutually perpendicular sort of elliptic shaped lines of curvature. And hopefully that will be reminiscent of a planar story that you're familiar with. So recall in the plane, that if we take two foci and we look at the ellipses generated by these. Okay. And we also look at the hyperbolas, which have these as their foci. Okay. So that's a situation we're looking at the differences between distances to the foci being constant. Okay, there's one like this, and then there's various. Okay, so this is sort of two families of sometimes called confocal quadrics. Two families of confocal conics. Okay, and the story here is that these are all perpendicular. You may have run across this in complex analysis. If you look at the function, say f of z equals sine z, and you look at what it does to the axes, the image of axes, you can get a story like this. So kind of a natural question is there a three-dimensional version of this? Is this part of a three-dimensional version of that? Somehow. And it turns out remarkably that the answer is yes. There's really a three-dimensional analog of that of confocal quadrics that goes also some way to explaining this picture. That was discovered by a student of Monge, and we'll talk about him next time, Charles Dupin, who was a very brilliant geometer and discovered lots of lovely things, some of which we've already talked about. We've already talked about Dupin's integratrix, but we'll talk about some other contributions that he made next time. So see you then.